right. I guess we can start. The homework is for tomorrow, so check them out. I hope you all had a nice weekend. We are going to talk about compactness. That's what I just mentioned a few words about it at the end last time, but that's our real goal for today, is to talk seriously about compactness. I hope that you remember from real analysis, in our subset of the real numbers, a compact set is closed and bounded. That's the Heine-Borel theorem. But compactness, the concept of closed, of course, makes a lot of sense for us, but bounded is not something that you can talk about in a general topological space. And so our definition of compactness, you could also talk about in terms of sequences, but we are going to try to avoid sequences as much as we can. We're going to talk about compactness in terms of covers, open covers, and finite subcovers. That was the other variation, or the other sort of conceptual framework that you talked about compactness in analysis. Probably the one you liked the least, but that's the one that is the most topological. So that's what I'm going for. So just to refresh the basic definitions, given some set, A subset of a topological space, an open cover of A is a collection of open sets covering A. By covering, I mean, i.e., A is a subset of the union. Sorry, I didn't give it a name. Open sets, I'll call it O. Our book uses like a script O, which is why it has a little curly thing on the top. That's my script O. Such that, sorry, I didn't mean to write the O right there. I meant that A is a subset of the union of all the U's, such that the U's are in O. That's what I mean by covering A. That is to say, when you take all the sets from your collection of open sets and union them up, they cover A. So, the picture you should imagine is A looks like this, and these sets from O are all sort of open sets like this that cover everything up. You can make them really big if you want. Something like that. That's a typical picture of an open cover. It is just a bunch of open sets which cover up all the points of A. All right? Did I miss one right there? Maybe. Needs a little guy right there. Okay? That's an open cover. And compactness is all about open covers and finite subcovers. So a finite subcover of an open cover. If you start with a big open cover, by big I mean maybe it has infinitely many sets in it. A finite subcover just means you pick only finitely many of those things, but they still cover A. So a finite subcover of O is a choice of only finitely many sets in O which still cover A. All right, so A might use infinitely many sets to begin with. A finite subcover would be you can choose only finitely many of those sets and they still cover all of A. All right. This may not even be possible, depending on what kind of set you're talking about. There may not be any finite subcover, but maybe there is. All right. And then the definition of compact, we say A is compact when any open cover has a finite subcover. All right. That's the definition of compact. Any open cover has a finite subcover. This, in my opinion, is a very weird concept, and it's not obvious at all what this has to do with anything. Unlike, say, connectedness, I feel like is a very ordinary type of concept, and it's obvious why connectedness is important and interesting. I would say compactness is not at all obvious why this would be important for anything. It turns out to be extremely important when you're doing topology. And the history of the idea of compactness actually is more complicated than this. People didn't come up with this open cover, finite subcover definition for a long time. Compactness had been discussed far earlier in terms of like closed and bounded, or in terms of sequences. But it was only after much reflection that people decided that this open cover, finite subcover thing is actually what's most topologically important about this. All right, anyway, that's what the definition of compactness is. I want to do several examples here, and then I got some for you to try, of demonstrating that certain sets are not compact. So A is compact when any open cover has a finite subcover. Can I just say A is not compact? This is not really part of the definition, but just what does it mean to be not compact? That would mean there is some open cover, but it does not have a finite subcover. So A is not compact means there is some open cover with no finite subcover. Right? That's what it would mean to be not compact. What that would mean, that would look like something like infinitely many sets covering A, where you really need infinitely many. You cannot just do it with only finitely many of them. Infinitely many sets covering A, where you really need infinitely many. Right? That's what it would look like if your set is not compact. It can be covered by infinitely many sets, but you actually need to use infinitely many sets. You can't do it with some finite sub-covering. All right? So I think we talked about one example of this last time. That was, I used the example of real numbers. Say A is the set of points 1 over n, where n is a natural number. That looks like, 1, a half, a third, a fourth, etc. It's these points approaching but not ever reaching 0. And then the open cover that you can use, which has no finite subcover, would be something like, if I take open intervals, I can use O as the open intervals. If I just take the intervals, say 1 over n to 2 each time, you have to actually cover all of these points, but what that would look like is 1/2 to 2 is like that, and then 1/3 to 2 is like that. These are my sets from the covering O, right? This is 1/2 to 2, this is 1/3 to 2, etc. And I believe it is true that each of these red dots eventually is going to be in one of these blue sets. All right? Like this red dot here at 1/2, it's not in this one because I exclude that endpoint, but it is in this one. All right? So these blue guys, they do actually cover up all of these dots. So those are the open intervals, 1 over n to 2. All right, so sets from O, oops, I'm still blue. Sets from O, first of all, they are open sets, right? Because they're intervals, and they cover A, because every one of those red dots eventually lies in one of these blue intervals. But the question is, can I still cover A by using only finitely many of these intervals? Is it only like, maybe I only need like 4 of them or something? The answer is no. If you take only finitely many, you're always going to be missing some of the points that are close to 0. So these guys here have no finite subcover. So sets from O are open and cover A, but we need infinitely many to cover A, right? Because no individual one actually stretches all the way and gets all the points. So that means, so this O that I said has no finite subcover. So that means A is not compact. This is an open cover with no finite subcover. All right. I hope that makes sense. There's actually a kind of a strategy that I used to choose those intervals. I chose these intervals so that they would sort of stretch out in a way which approaches where these points are also approaching. That tends to be a good idea. So this is a very vague bit of advice, but here's my pro tip, is to choose open sets that are somehow like stretching out to the boundary or something like that. Something like that. Choose open sets which sort of gradually approach the edge or the boundary or something like that. This is vague advice, and you have to know what you're looking for, which comes from practice. But for example, why did I make them stretch towards this end, the left end, rather than the right end? Well, I think you can tell this. If they stretch towards the right end, there's only one point there, so you don't actually need infinitely many things if you're trying to stretch them out towards the right end. But if you're stretching out towards the left end, then you do have this issue with there being infinitely many things over there. So there's some amount of practice that it takes to kind of see what you want to do. All right, this is my basic example. Let's try some more examples, and then like I said, I got some for you to try out. How about this set, just the open interval 0 to 1? Is it compact or not? It is not. I'm here to tell you, this is not compact. And I want to do a similar kind of thing. So what does it take to demonstrate this? You have to tell me an open cover, which I'm going to just use intervals in this case. You have to tell me an open cover which has no finite subcover. So I'm going to say let O be the cover using intervals like actually the same intervals from here can be used in this same example, but just to make things a little more interesting, how about I will use a slightly different one. How about just 0 to 1 over n? All right, so in this example, my entire set is this open interval, and the open cover I am using takes intervals like this. I didn't mean that, 0 to 1 over n. That's not a... I did mean that. Did I? No, I didn't mean that. If it's 0 to 1 over n, can I just say, how about this? I totally meant this as a bad idea example. Sometimes you got to do bad idea examples, right? What's wrong with this example? The open cover, the first one would go all the way 0 to 1, and then the next one goes only halfway, then only a third of the way, then only a fourth of the way, etc., right? And now I say something like, remember the point of this is that all these sets together cover up the interval. Actually, that's true. If you look at the union of all of these things, you do get the whole red line. Do we actually need all of them to cover the whole thing? And the answer is no. That's why this is a bad idea example. Because actually, you only need the first one, right? The first one all by itself already covers the whole thing. So is there a finite subcover? The answer is yes. I can still cover it using only one of them. And so this is not a good choice of the open cover. So this one, this has a finite subcover. So it was a bad choice. Does that mean it's not compact? Or does that mean it is compact? I'm trying to show that it's not compact. If you say it is compact, it means every open cover has a finite subcover. Just because I showed you an open cover which has a finite subcover doesn't mean that it is compact. It just means that was perhaps a bad choice of the open cover. Anybody see how could I modify this? This is actually not what I meant. You want to make it so that gradually stretch out, eventually filling up the whole thing, rather than I had one that already filled up the whole thing and I shrunk it down. That's the wrong idea.
1 minus 1 over n?
0 to 1 minus 1 over n? Yeah, that's a great. So let's try instead. So all of that was a not entirely bad idea. How about let's try, if I were to write specifically the interval 0 to 1 minus 1 over n. Yeah, where n is a natural number. Here I wrote O as a set. Remember, O is a collection of all of these intervals, so you can make it a set if you want to. It is the set of all intervals that go from 0 to 1 minus 1 over n. Now the picture, this is what I meant to say the first time. Now it looks like first one would be actually 0 to 0, doesn't make a lot of sense. That's nothing. The next one goes 0 to a half, then 0 to 2/3, then 0 to 3/4, etc. And now it is the case that these intervals, they do fill up the entire original set, which was A, this open interval. So this is an open cover. With no finite subcover. Excellent. Any thoughts about that one? This is an open cover with no finite subcover. All right. What about if it was the closed interval? If that A, instead of an open interval, was a closed interval, can you do a similar kind of a trick with that? So what about, how about A is the closed interval 0 to 1? All right. So that's this. I'm trying to write A in red. That's this. Now I could, remember it has to be an open covering, so the sets that you use here, they have to be open sets, all right? Which is going to complicate matters a little bit. There are a few ways you could try to modify the previous approach though. So one way would be, I could just do this thing. This is what we did before, right? Eventually, like approaching, but not getting to that point. What's this actually is not a legal open cover. Can somebody say why? What's wrong with that? As just using the same thing from before?
It doesn't cover 1.
Yeah, this doesn't cover this point, and also it doesn't cover 0. Now I could easily make it cover 0 by just moving everything slightly to the left. So that would, originally this looked like 0, 1 minus 1 over n, right? Now I could just change this 0 here to something like minus a half. That would basically push all of these guys over a little bit. What? I missed that. I was trying to be cute and it didn't quite work. Like that, right? Now it covers 0, but actually it's not going to cover this point. How could we fix that? Anyone have a similar trick? Maybe I could push the right endpoint to the right a little bit. I just tried to slide everything, make it stretch a little bit further to the left. I could also make it stretch a little bit further to the right. Maybe this instead of 1 minus 1 over n. How about let's try maybe minus a half to 3/2 minus 1 over n. That makes it so that these guys actually do stretch. Eventually, they do stretch beyond 1 because they are going to approach on the right side. They approach 3/2. All right. So what that would look like is these blue sets now. Eventually, they will go past there, and then just continue. Eventually, approaching 3/2, right? Instead of approaching 1. Is there a problem with that?
Is it still infinite?
Yeah, you should be concerned about the finite subcover business. Remember the whole point of choosing these intervals here is you actually need to use infinitely many of them because you need it to stretch all the way to the end. Do I need to use infinitely many of these intervals? I think you don't. Actually, at a certain point, on my picture, it looks like this one. Actually, this one already includes everything, right? And so you don't even need any of these. So this covering here, This one actually has a finite subcover. Because eventually you get to, if say n is 4, it's going to be minus a half, comma, 3/2 minus a fourth. And that already includes the whole interval, 0 to 1, right? 3/2 minus a fourth is 1 1/4, whatever that is, 5/4. That already includes the whole thing. So you don't need infinitely many of them. You only need this one, just one of them. So the unfortunate answer is this whole thing was a bad idea, and it's because actually this is compact. So it's a fact. It's not easy to prove, but we'll get to it eventually. But this set actually is compact. Any open cover you can choose will automatically have a finite subcover. This is not obvious in my opinion, but I mean, if you try and play around with these intervals, you will eventually give up and realize that you probably can't do this in any way. So I'm going to say actually A is compact. I said it's hard to prove, although if you remember anything from real analysis, compact is equivalent to closed and bounded, and A is a closed interval and it's bounded. So I suppose you already knew that it is compact. That means this game that I'm trying to play with the finite subcovers actually is not possible for that set, because it is a compact set. All right. So can I just say this is hard to prove using covers. If you know the Heine-Borel theorem, you say it's closed and bounded and that's it. But this is hard to prove using covers. You would need to somehow prove that all open covers have a finite subcover, and that's not easy to do. Right? Because you have to somehow imagine any possible way of covering this up with intervals and then argue that you would require infinitely many of them. Okay, let's just try a few more. So that one is compact, so you can't say you can't find this open cover with no finite subcover. How about in more interesting settings? How about in R2, the x-axis? So that's this set here. Can we make an open cover with no finite subcover? Oh, sorry, I skipped an example that I wanted to do. That's all right, I'll come back to it. Can I make an open cover with no finite subcover? Now, I've been using intervals in the other examples because that's what open sets in R look like. I'm talking about R2 now. The sets that you use should be probably balls, open balls, which look like circles. Or, I mean, you could, there's some cases when you want to use other weirder looking open sets, but you might as well. Can anybody think of a way to choose, cover this up with individual balls, little, circles? They don't have to be little. They could be big if you want. So that you actually need, the idea is you make these balls, I said make them stretch out to the edges somehow. Now this doesn't even have edges, but that might give you a hint about where you want to put the balls. Any ideas? I have two different natural ideas and both will work. Oops. Think about overlaying, balls on this thing so that it grabs, covers every point in a way that you actually need infinitely many of them. Yeah?
I was thinking like you start small and just get bigger.
Start small and get bigger, yeah. This is one of, I said I had two ideas and both will work. She said start small and get bigger, like here, 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 here. This, I think, fits very nicely into my general suggestion of make them stretch out to the edges. There's no edges, it just goes out to infinity in this case. But yeah, if these are your open sets, so the way I would write this is, as a set, it's the ball around 0 of radius n, right? That's the notation. This 0 is 0, I guess, I mean the origin. Maybe I'll write it as a 0 vector. It's the ball around the origin of radius. You start with the radius 1, and then radius 2, and then radius 3, etc. These are increasingly large open balls. And they do cover the entire x-axis, because any point of the x-axis eventually lies within one of these balls. There's infinitely many of them, of course. And then, is there a finite subcover? The answer is no. If you only take finitely many of these, they're not going to cover the entire x-axis anymore. So this is my open cover. This covers the x-axis. But we need infinitely many to cover it. So there does not exist a finite subcover. Great. I said I had 2 ideas. That was one of my ideas. Anybody have a different idea? You can actually do this using this is using a bunch of balls centered at the origin of increasing radius. I had another idea where you can do it using all kind of the same size balls. Anybody have another idea? I'm gonna say or. Any other? So this way, you could also do something like this. Cover it up with balls in this way. Right? That would also be a covering of the entire x-axis. In complex analysis, this is the real axis. That's what I meant to say. This will cover all of the x-axis, and then it is still true, you need infinitely many of them to cover the whole thing. They have some overlap with each other, but you still need infinitely many of them. So in this case, I would say the balls that I'm using would be ball around n of radius. I think you have to use 2 or something like that. That's so that, no, you can use 1. You don't need 2. Whatever. I mean, you can use 2 if you want to. The ball around each number of radius 1. So the first one, if these are the numbers, right? 1, 2, 3. I'm talking about this ball, this ball, this ball, and so on, right? That covers the entire x-axis, and it has no finite subcover. All right. Either way, we'll get the job done. This example here suggests a general fact, and that is, I think, really both. I'll just focus on this picture here. You can do a similar trick on any kind of set that stretches out forever, right? This set, if it goes all the way out, sort of to infinity or something, then you can always put these little balls around every point, and then there cannot be a finite subcover because you need these little balls to stretch out to infinity. Maybe it's actually clearer in this example. If the set stretches out to infinity, you can use this covering, and you are guaranteed, as long as the set stretches out to infinity, you're guaranteed that this does not have a finite subcover. So I would say in R2, or actually any Rn, any set stretching out to infinity, what I mean by that is maybe I should have just said it this way in the first place, any unbounded set. Any unbounded set in Rn, you can use that. It can be covered by the first one that Julia said. ball around 0 of radius n. That's this one. Right? No matter what your set is, it will be covered by those circles. Eventually those circles cover, that covers all of R2, so any subset. But if your set actually stretches out to infinity, then that means that no finite amount of these can ever cover it. So any set stretching out to infinity can be covered by this with no finite subcover. All right, so that means in Rn, any unbounded set is not compact. Because an unbounded set, you can always use that sort of bullseye type cover. And if it's unbounded, it means you cannot use only finitely many of those bullseye type sets. So in Rn, any unbounded set is not compact. And this actually looks nicer if you write the contrapositive of that. So maybe I'll write that as a theorem. In the contrapositive, it says in Rn, compact implies bounded. That's the contrapositive, right? This says unbounded implies not compact. The contrapositive of that is compact implies bounded. And this is actually sort of half of the Heine-Borel, right? The Heine-Borel says compact is the same as closed and bounded. The whole Heine-Borel is a little tricky, but this is part of it at least. All right, a compact set is automatically bounded in Rn. This only, unfortunately, this boundedness only really makes sense in Rn. If you have some other topological space that's not Rn, then it may be that you don't even know how to talk about boundedness, because boundedness has to do with distances from the origin, and that it's not always possible to discuss in a weird topological space. All right. I had one more example. How about another R2 example? And then I have some for you all to try. How about another example in R2? Let's try the unit open disk. That would be sort of this set, the inside of the circle, not including its boundary. Ooh. The unit open disk, that means this interior of the circle in R2 without the boundary. All right. This also is not compact. Can we make an open cover here? I want to use, I'll give you a hint, some kind of ball of something something. I would like to use balls in there, which somehow, abiding by my pro tip from before, make them stretch out to the boundary or something like that, stretch out to the edge. Anybody feel inspired? It may be easier to draw a picture of them than to describe in words, than to write as a set. But can anyone say, like in words, what your balls should look like? You got something? Yeah?
It would be that they're going from the origin, the radius is just approaching the other.
Yeah. Yeah, right. So it's something like that sort of bullseye picture, but the radius of the balls is stretching out and approaching 1, not going out to infinity. Yeah, so it's like, this kind of thing, getting bigger. Eventually, that looks terrible. Eventually approaching, but not ever quite reaching the outer edge. That looks like some kind of spiral, which is not what I meant. Yeah, that's what I want. How would we write the formula for that? The ball of certain radius, or a certain, first goes the center point. What's the center point of these balls? Yeah, it would be the origin. I think they all have the same center. That's easy enough. And then what's the radius? You want the radius to approach 1. Yeah?
1 minus 1 over
1 minus 1 over n. Yeah, if you remember, that's sort of one of your favorite sequences from real analysis, which approaches 1. From below, right? I want it to be less than 1, but approaching 1. Yeah, great. This is the unit open disk is not compact. That is an open cover, and why this has no finite subcover. Great. All right, I got some for you to try. So your job in each case is show it's not compact by, what you have to do is you describe an open covering and then say, say that this open cover has no subcover. So show it's not compact in each case. As I said before, to show something is compact is quite a bit more complicated, and to be honest, usually I use the Heine-Borel theorem if I'm in Rn, and if I'm not, I walk away or something. It's harder in that case, but we'll get to that eventually. But anyway, how about the interval from 3 to 5 in R? How about the unit square? Open unit square in R2, like that. I mean, it contains none of its boundary points, but it's just, if you like, you could write this as a product, 0, 1 cross 0, 1. It's the product of 2 open intervals. The open unit square in R2. And then I got one more. I got 2 more. I should make them red since I've been making all my other sets red. This is in R2 sort of a cross, a horizontal interval and a vertical interval, just kind of the union of a horizontal interval and a vertical interval. And then the last one. This last one is what they call a punctured disk. It's a closed disk, so it has its boundary, although that's not really important. What's important about it is the puncture. That is, this does not include the origin. It includes the whole disk, but it's missing that one point in the middle. That also is not compact. All right, see what you think. I'll give you a few moments. We got about 13 minutes remaining, so maybe we can work on these for a few, and then we'll talk about them. I think that last one is a little tricky. The other ones, well, they're all a little tricky until you get used to it. I'm going to suggest maybe doing this one. I think this one's a little easier than the square. I don't know. Doesn't matter. That looks good.
Just makes sense if you make the balls like squares, but they're
approaching
Yes.
one.
In that case,
Yeah, it'd have to
don't
be-
say B. B means like an actual round ball.
Okay.
But if you wanna do that, then it makes
Also, that N
squares.
is right, cause it's the,
Right.
it has to go to one, right?
Mm-hmm, yep, okay. Doing okay?
I haven't gone very far yet.
No, no, do you do the first one? Mhm. We could be inspired by our other examples of the. Yes, that's great. All right. Maybe the square is easier than that other one, I don't know. Okay. Yeah, that looks good. Everybody's saying this is actually not my answer, but let's see what it is. That's good. It looks like everybody thinks the square is easier than the other one, but that's fine. This happens, especially the first time I teach a class, which is, this is the first time I taught this class. A lot of things that seem obvious to me are not, and things that seem obvious to you are not obvious to me, and the other way around. We're all God's children, just trying to get by. All right.
This one could just be a ball of material. They are in cross, like,
Mhm.
are they both the same, like what they
Yeah,
are?
yeah, let's say it goes out to 1 each time, yeah. Line. Oh, yeah. This one's tricky because you actually can't exactly use them. Because of all,
For
it's
cross, is it just the same thing
but
as
you can use some other
Yeah.
shape and set.
But then for this one, it's not including zero, because I think this includes one, so like, okay, from 1 to 0, we do it backwards. And approaching 0. Or not?
How's it
No,
going?
because then it'd start from there. The last one, well, this one is just like one of these, right?
Yes,
Okay.
yeah.
But then for,
It's more like the one you use for that.
yeah,
This one goes out further.
but for this one, it's not including 0, right?
Mhm. Yeah, so for that one, I would say it's easiest to use sets which are not balls. Some other kind of open set. Another shape. Maybe round. Don't use squares or something, but not a ball. Alright.
Yeah, that's the thing. Could you do like,
That's a good idea.
kind of
Donut
like
shaped things, yeah.
a,
Really, an open set, you
like a
can use
donut?
basically any kind of shape without its
So then
boundaries.
just make,
That will make an open set hard to.
make a cell like small and small.
So such a thing has like an outer radius and an inner radius. If it say like the outer radius is 2 and the inner radius is 1, then you could write it as the ball radius 2 minus the ball radius 1.
Subtract from each other. Like you just start it out as like they're the same size, so it's just a line on the top.
That's a cute trick. You could just
Small,
write
center's
the
good.
donut. You
Small.
would write words or something.
Does that make sense? It's just
Any ideas?
could you make it? It makes sense to me, like, it's 2 balls subtracted from each other, and then you just keep making one center small and small.
Mm-hmm. I like that. Yeah. outer boundary is included.
It's,
Yes.
Oh,
Makes
you're
it
right, the biggest
a little
one.
more interesting. If the outer boundary is not
I
included,
gotcha.
those are just growing circles, and then
Oh,
the hole in the middle would
Be
matter.
0, 1.
Yeah.
sure.
But then
That could be good.
Anything for the last one?
Be on the way to make it so small, it's also the
It's a little tricky. My hint
For
is
this one, isn't the
don't
one-
use,
isn't the
can't
boundary
really use
hidden?
balls. It has to be some other kind of shape.
Okay.
That's
So this
the
doesn't-
sense object.
Oh.
I'll give you one more minute and then we'll talk about it. Write down some.
If the donut thing I'm thinking about is talking about the inner, like,
0,
the radius has to be so
1 minus
small.
x.
How will it just have the 0 and nothing else?
Mm-hmm.
Yeah, but I know what you're saying, that's supposed to be
Generally, you make
Yeah.
shapes which
Right.
sort of
right.
stretch
Is
out
it
till
one
they
minus
make,
it, or
look at
is it-
this one, you have
They just want
circles
0, 1
which
to get to 0.
get
Oh, right, it's not 1 minus
bigger
1.
approaching
Right.
these things.
So this is.
So I have to make a problem.
Oh, use little crosses, okay. That's fine. That's actually not this. Let me use this cross.
Oh, no, yeah.
That cross itself there makes a box.
Oh,
But actually, that still works. So really what you need is boxes, which
go.
which is still fine. I mean, it still works. Yeah. So I would say here, you want themes which are flowing, but in this case, they're flowing inwards towards the middle, right? Rather than going out, because what we want them to approach is like the whole the point. All right, I think we got to talk about these. So people did great on the first one, the interval 3 to 5. Here, I would use the open cover, something like, interval 3 to 5 minus 1 over n. This makes it so that the right end point of these intervals approaches 5. So I saw some slight variations on that. You could do 3 plus 1 over n to 5. I don't think anybody did that, but that would also work. Right? This one would, everything goes all the way to 5, but then the left side approaches 3. Or you could even, if you want to be super fancy about it, 3 plus 1 over n, 5 minus 1 over n. This makes them grow, doesn't matter, both ways, whatever. I would say the first is the most natural. Okay, and then the square. All right, people said this is a great idea that everybody had that somehow I didn't have. They use the open cover was a product, 0 to 1 over 0 to 1 minus 1 over n cross 0 to 1 minus 1 over n. This is great. That is, this would look like on the picture, it would look like open boxes that are getting bigger and bigger, approaching out to the edge, right? Excellent. The cross up there were a few answers that I saw, but I think most people ended up just using the ball of radius centered at the origin of radius 1 minus 1 over n. This makes this kind of bullseye style balls, which are approaching those 4 points. And that's all you need. You could also use, I saw some people used boxes, like rectangular boxes. That would be the interval minus 1 minus 1 over, plus 1 over n to, am I doing the right one? Yeah. 1 minus 1 over n, something like this. And then the same thing again. This will make squares that go like this, eventually approaching, this set that you're looking at, right? Same idea, using boxes instead of circles. That would work also. My idea for this one, actually, I thought this was going to be like a tricky, cute example, and everybody came up with a much simpler solution than I had in mind. What I had in mind was, see if you think this is cute or stupid. This is my original set. I use the same bullseye thing with radius approaching root 2. And this covers the whole square, but approaching that corner point. And so you need infinitely many of those sets. Are you impressed, or do you think that I'm being needlessly complicated? This seemed obvious to me because I had just done this one, and I realized, oh, I can just do the same thing again, and it will still work. And it's true. You can just do the same thing again, and it will still work. You have to stretch the radius a little bit. All right. What about this one? This one is more interesting, maybe, because my hint that I gave to everybody is you can't really use ordinary balls like as the whole set, because an ordinary ball will have the center point in there. Certainly, if you take a ball centered at the origin. Oh, sorry, it's time to go. What some folks came up with was sets that look like sort of a donut type shape. This is called an annulus. All right, that is like that, and then you make it so that this outside radius stays like it is every time, but the inner radius, as you go down the sequence of sets, approaches the origin. And the cutest way to write this would be, what I have written here is something like the ball around the origin of radius 2. That's the outer one. Let's just say the outer one goes out to 2. And then you take away the ball in the middle. This would be, say, minus the ball at the origin of radius 1 over n, say. And so as I continue taking away the inner ball, this makes the inside shrink down. Can somebody say, actually, there's a slight error with this? This is not 100% right? I know it's time to go. Yeah?
How does it contain like the boundary of the circle in the middle?
This inner blue circle, you mean, or that?
Yeah. Like how does it cover that? Is that red line solid?
This right here is not really a red line. It's just a single point is missing. So this, yeah, you don't have to worry about that. The problem is this: when I subtract the inner ball, what you get is this set, including this boundary, because I've subtracted an open set, and so it leaves behind the boundary of that. And so the problem with that is this is not an open set. And when you're doing an open cover, it has to be an open set. So instead of that, technically, you subtract the closure of that. And that makes it so that this is still an open set. That's a technicality. All right, great. Sorry to go over by a few minutes. See you all tomorrow. Let me know if you have homework questions.